Okay, yes. Hello, everyone. Today, Kadri Ilker Berktav is going to give the first talk on a sequence of talks on introduction to derived geometry. And today, he's going to tell us about basics of infinity categories.
Yeah,
Please.
thank you. Is this visible? You can hear my voice, I guess. No problem, right?
Yes.
Okay, cool. So thank you for the introduction. And as you just said, this is the first lecture, and actually our purpose is the study. I don't know, to introduce the drive geometry, but essentially we will focus on drive algebraic geometry. Of course, to do this, we need to use the terminology of infinite categories. I mean, to some extent, at least. And then in this talk, essentially, I will present possible different notions of infinite categories, and so that at least at the end of the day, you may have a kind of idea how to think of infinite categories. Okay, so I will present different possible approaches. And next, of course, we will discuss how to build infinite categorical spaces, let's say drive spaces. And then we will present how to introduce certain geometric structures on those things. But for these things, we have some background on this infinite categorical framework. Okay, so this part of the talk, I will use a couple of slides. Okay, and I will just give you certain, punchlines, key ideas from the literature. So it's a kind of an informal part of the talk, and then I will use the whiteboard for more technical details. Okay. So first of all, I will follow, I mean, if you want some overview of literature and key ideas, I will follow Lurie's Higher Topos Theory book. I mean, of course, it's a huge book, but there are nice other, I don't know, resources I may suggest. One of them is the second one, An Introduction to Derived Algebraic Geometry. It's a nice lecture note. And also, if you want more intuitive approach, you can look at what is an infinite category paper. These are nice sources, I guess. And we will follow two main approaches, actually. One of them is by using topological spaces, actually. And the other way of discussing infinite categories is using the language of simplicial sets, actually. Okay? A very special kind of simplicial sets can be used as a model for infinite categories. Okay? So let's start some key ideas informally. So when somebody talks about infinite category, so you should understand, okay, this thing is a kind of a generalization of the usual category theory or usual categories. And once you adopt infinite categorical language, it means the usual ordinary category is just a one category, okay, in that language. Okay, and you will have some objects and morphisms, just like in the case of ordinary categories. But the additional data is like you will have, let's say, the k-morphisms, and leading to kind of, you have a machinery like more maps between maps. Okay, and somehow you have enough framework to capture this kind of property. Okay, so we will discuss the details later. But there are some issues. The main issue is composition in that infinite category is not actually well defined. So it is always up to something, and we will see up to some equivalence in your structure. And these things are useful if you want to do homotopy theory in your category. Okay, so this one is actually important one because the derived algebraic geometry is actually combination of the usual algebraic geometry together with the homotopy theory. Okay, so therefore it's a kind of a homotopical extension of the algebraic geometry, okay, the derived algebraic geometry. Good, and the other thing, another maybe informal way of saying that, if you look at the formal mapping spaces, in general for ordinary categories, these are sets. These have the structure of a set, but now mapping spaces are more than a usual set. Okay, you have more structures actually. And then there are many equivalent descriptions. So I will just mention some of those. I mean, if you want to attend some, I don't know, derived geometry meeting, you can use the following notions, to make a interaction with those guys. So it's a kind of a bluffer's guide. So one possibility, conceptually, the easiest way of thinking those things, using topological spaces and using topological categories. Okay. So conceptually easiest model. And for this model, when we say topological category, we mean this home space, this mapping space, has the structure of a topology. Okay, this is more or less the key idea. There are other details, of course. And the composition has, I mean, it is a continuous operation. Okay, you have a composition in your category. And this is the conceptually, we will see why, the easiest model, if you want to define infinite categories, this is a very useful approach. But there are technical details. If you want to do some computations, if you want some combinatorics, combinatorially efficient model is the use of simplicial sets actually. Okay, so when you use simplicial categories, in that situation, the same logic, so the mapping space as a structure of a simplicial set, but usually we will use a very special kind of simplicial sets, what we call Kan complexes. We will discuss those things. But we have another approach, the easiest to build. Actually, this is the easiest one. Actually, I will discuss this model first. And for the other ones, I will use more technical approach. This is called the relative categories. I mean, the relative category, it's easy to describe. You just tell me a category along with a subcategory W. Okay, you introduce a category C and a W. Okay, this is called the relative category. Very easy to build, easy to consider. And okay, let's see. And okay. Anyway, so let's look at these things. So in case of relative categories, the important thing is somehow you need to introduce a very special type of maps in this W, right? Remember, we have pairs, C and W, and these maps is kind of, let's say, equivalences, and they provide a weaker notion of isomorphism. Okay, somehow you want to find a weaker notion of an isomorphism in your setting. Okay? Examples are, for instance, examples of this omega W in your pair. For instance, in the category of topological spaces, these are homotopy equivalences. In the category of chain complexes, these are quasi-isomorphisms. And in the category of CDGA, means commutative differential graded K algebras, okay, over K, over a field, and we somehow are interested in the ones concentrated in non-positive degrees, and quasi-isomorphisms will give you that notion, okay? And for us, the third one will be the most important one when you define derived schemes and find derived schemes and everything. And of course, if you look at carefully, if you want to specify an infinite category, this is the easiest way. Okay? You can say, okay, this is my category and this is my W. Okay, so very little data you need. And once you choose weak equivalences in your category, the rest is automatically determined. Okay, so the easiest informal way of, I don't know, specifying an infinite category is introducing this, your W. And especially we will use this approach in practice. It's very useful. And a very particular way is you can use model categories. So if you look at carefully, this is almost like a model category, right? It has a model category structure, but model categories are actually very particular relative categories. So if you want to use model categories, so the model category structure is one way of introducing such a structure, okay? So therefore, a model category is actually a relative category. In addition to this W, you introduce the other two choices of classes of morphisms, what we call fibrations and cofibrations. Okay? So therefore, so instead of fibration and cofibration, you can directly consider relative categories. If you want to use model category, this is still a relative category, but in which you have two additional data. Okay? And of course, I'm not going to give you the other these axioms. So there are many axioms, so you require extra list of axioms. But let me just give you 3 examples. And for instance, any category with limit and colimits, your fibrations and cofibration are actually all morphisms. All morphisms turns out to be fibration and cofibration. And weak equivalences are just isomorphisms. Okay, so this is kind of a trivial example. And the example we are going to be interested in is the CDGA. For instance, in that case, your weak equivalences will be quasi-isomorphisms. And if you're not familiar with that notion, this is like You don't have an isomorphism, for your CDGAs, between your CDGAs, but you have isomorphisms between the level of cohomology. Right? So instead of an isomorph, you are not saying A and B are isomorphic, but they may still have isomorphic homology groups. Good, so therefore this is a weak way of defining sameness. Okay, so you want weaker notion of isomorphism. And the fibrations turns out to be degree-wise surjections, and the cofibrations turns out to be maps with, okay, whatever it is, left lifting property, if you are familiar with these things. But it's enough to mention, let's say, these two. For topological spaces, weak equivalences. CDGA is commutative differential graded K-algebras. So I will come to that, actually. I will give you the explicit description. So it's like, instead of a usual algebra, you have a grading, and you have a kind of a chain complex. So therefore, you have a differential. Okay? It's like you have a grading, and for each homogeneous degree, so let me use, if you want, let me show it here. Actually, we will come to that. So A is like, you have some gradation like this, okay? And each AI is a K vector space. And also you have the differential, satisfying Leibniz rule and everything. Okay? So anyway, so for topological spaces, your weak equivalences are homotopy equivalences. We will see why this is important. And the fibrations are maps with homotopy lifting properties, and cofibrations are the maps having homotopy extension properties. Okay, so these are a very rough picture. And as you see, using this relative categories, it's easy to specify, easy to study with these examples. But actually, we will focus on the other approaches as well. So the next part will be about, how we define infinite category using topological spaces and simplicial sets. Okay. So any question so far? So far, so good. So now I don't need this one. Oh, yeah. This is some electronic thing. Bu mu? Bu değil galiba, değil mi? Okay. Okay. And we don't need this. Okay, so let me close this. Kapandı. Okay, good. So let's. So after these, I don't know, certain punchlines and informal slogans. So let's study with the following. So following perspective. So infinite categories using topological, let's say, spaces or topological perspective. Okay. So let me start with a motivating example. So motivation. So let's start with two topological spaces. X and Y are topological spaces. And also let us consider two maps between these two. Okay, continuous map. Your morphisms in that category, continuous map. And let's consider a homotopy between these two. So let me recall you what is homotopy. So a homotopy, right, is from F0 to F1. It is a map, right? So let me denote F, X, 0, 1, Y, and actually, so for each xt, we have ftx, right? And here, if you restrict when t equals 0, right? So it is the original map, F0, and you have continuity and everything, so something like this, right? So this is your homotopy. So if you want some more diagrammatical picture, so you have x, y, and you have two maps, F0, F1, and you have this Ft map, and you have this family of continuous maps, okay? Family of continuous maps, deforming, you know, F0 to F1, okay? Deforming F0 to F1, whatever. So this is your homotopy, if you are not familiar with these things. So let's make the following observation. So in algebraic geometry, in general, we define an equivalence relation so that we are saying these two continuous maps are the same if they are homotopic. Okay, so in general, we consider homotopic maps. So identify homotopic, a pair of maps. Okay, in general, we are doing this, and also in algebraic, maybe I should say algebraic topology. Okay, and we also study equivalences, but not an isomorphism, but homotopy equivalence instead of the usual isomorphisms in your category. In that case, homeomorphic, right? So now we have a nice example. For instance, in algebraic topology, the point, right? You have a point and a disk, right? D2. Of course, they are not isomorphic in that category, but they have exactly the same homotopy type because you can, you know, deformation retract this thing and you can obtain a point. So same homotopy type, but not isomorphic. Right? Another possible example, you may consider a circle, and you can consider R2 without origin. Right? These are some standard examples, right? Standard textbook examples. And you can really embed this S1 here, right? So you can use this inclusion. So S1. But also you can use a retraction. So you can define this, you can just squeeze this space, right? Like this. And you can obtain S1. So this is your retraction. And this map turns out to be homotopic to identity. So you have this kind of deformation retraction business. Anyway, so they have same homotopy type, homotopy type, but not isomorphic spaces. So why this is important? It means that their homotopy theory, let's say, will be the same. So instead of studying this thing, you can just replace all disk by a point, or you can replace all S1 with that one. If you insist, weaker notion of isomorphism, right? This is weaker than an isomorphism. And then you can study homotopy theory of these objects, and then you will have the same theory. So this is some standard examples. But you can do more. So this is the first observation, let's say. This is the first observation you can make. And the second observation, okay? And you can actually define a category, okay, by using these things. So you can form a category. Let's call it something like this. Okay, it has objects. Objects are continuous maps. Okay, so these are continuous maps. And what about morphisms? Are just homotopies. Okay, so like this. So therefore, if you have two objects like this is one object, and this is another object, and this is your homotopy. And this homotopy is actually a map in the mapping space of that category from that object to this object. Okay? You know, the home space, but now your category is this, and your objects are maps. But of course, the question is, I mean, this is nice, but can we organize this information? I mean, how to organize such information, okay, in a more clever way? So, how to organize such information? And the answer is you need a new notion, right? A new notion or notions later, right? Somehow, I don't know, encoding this maps between maps type situations. Okay. And one way of doing that is introducing two categories, right? So therefore we have a definition, let's say informal. So a two category is a category enriched over one categories. Okay. So what is the meaning when you have something like this? Okay, a terminology, a category enriched over something. It means that meaning your mapping space, your home space. Okay, let us denote this thing by C. Your home space is a category, is a one category. Okay, it has the structure of a usual category. Therefore, it has objects and morphisms. And therefore, the second level morphisms will be called the two morphisms of that two category. Okay, so this is the terminology. Good. And you may naively say, okay, inductively. Okay, so naively and inductively. You can do the same thing for n categories. Okay, so inductively introduce, for instance, let's say higher morphisms, and let's say n categories. Okay, so this is our next task. So this is the first motivation. So you can start with an argument like this, and you end up with this definition, and then you can ask the same thing. Okay, I can just keep the same procedure, and maybe we can define higher morphisms or discuss and n categories. So let's see an example, again, coming from topology. So let X be a topological space, okay? And we have this, let's say we have some number n between 0 and infinity, okay? And we define an n category, okay? An n category, or we define something, later we will call it n category, but informally, let's define an object like something like this, denoted like this. Here is the definition. First, our objects are the points, okay? The points of X. So therefore, it's like you have this topological space X, and your points are objects of that thing. Later we will call it n category. Okay, so what about the morphisms? For instance, morphisms between X and Y. Let's say this X and Y is a point of like this. Let's say X here, Y here. Okay, and these are defined to be the paths. Okay, path between x and y. Good. So it's like, or if you want, which means, so you have a path like this. It is a continuous map, right? This is the meaning of path from the interval. I don't know, let's say gamma 0 is x and the gamma 1 is y. Okay, therefore you have this path. Oh, image of this function gives you a path. And you can define two morphisms to be the homotopies. Okay, homotopies of paths. Homotopies of paths. Like you introduce, I don't know, this is your f, for instance. You may have some other path like this, g, and the homotopy between them, right, is your two morphism. Oh? And since you are dealing with these paths, so of course you can do the same thing. You can define, let's say, two morphisms. And this turns out to be homotopies of homotopies. Okay, homotopies between homotopies. So you may have exactly the same picture. And what if you have two other homotopies, right, deforming these two? And then you can, because homotopy is actually just define a map like this, right, using unit interval. But by just adding extra powers of that interval, you can define higher homotopies. So it's not a big deal. So therefore, you can just keep doing that. Okay, you can therefore define higher maps like that. So let's see what we have. And of course here, maybe we should note that, or remark, if this n is, I don't know, finite, right? Of course, you say 2n morphism. I mean, we say they are the same if there is a homotopy joining them. Okay. So let's say 2n morphisms of this thing, okay, are the same if and only if they are homotopic. Mm-hmm. Now, this one? Mm-hmm. Yeah. In that case, yeah, you're right. But in that example, we just stop at 2, like this. So there is no higher maps here. But I guess still to have associativity of composition. Ah, sure, of course. In that. You mean, okay, yeah. Something like this, k less than n. You're right. Mm-hmm. So the homotopy here are taking equivalent classes, right? So this is just still the same example. Still the same example, right? Still the same. What do you mean? So you mean? So two K morphisms are the same if they're homotopy. Yeah, it means that there must be some three morphisms as a homotopy, okay, and joining them essentially. So doesn't it change the set of K morphisms? Set of K morphisms. I mean, it's like yeah, yeah. And we just say, for instance, let's assume you have three morphisms, and we want to say them they are equivalent in some sense. And it is true if there is a four morphism joining them. So the four morphism is like homotopies between three morphisms. So the three morphisms are kind of homotopies between two morphisms. So two morphisms are the same if there is a three homomorphism, you know. So it's like define the category then. Actually say two morphisms are quotient set. Multiples of pets, modulo when you have a three morphism connected two things, you just declare it the same. For these things, yes. Similarly for yeah, yeah, yeah. Okay, good. And what else? This is the first maybe a remark. And the second thing, when n is 0, so when n is 0, what's happening? So when n is 0, you end up with actually pi 0. Okay? So this actually, I mean, this notation is kind of chosen intentionally. So this turns out to be the usual path components. You know, path components of x. And as you may guess, when n is 1, you recover the fundamental group pi 1x. Okay, so the usual notion of fundamental group. But actually, since you have fundamental group and you have invertibility as well, so therefore all maps are kind of, I mean, actually this is a groupoid, okay, because you have invertible maps. So therefore this is fundamental group, but actually this is a groupoid. Okay, this is what we call fundamental groupoid. With that motivation, this construction is called n groupoid. Okay, this thing is called fundamental n groupoid. So we just call the fundamental n groupoid. Okay. So if we go back, this is our inductive and naive way of thinking. You can define something like this. So definition, again informal. So therefore, an n category is a category enriched over, as you may guess, n minus 1 categories. Okay, so it means that as in the case of 2 1, right? So it's like now your mapping space has a structure of this example 1 category, but in that case means this thing, your mapping space, or maybe I should use home. Right, is an n minus 1 category. But I mean, you can easily object, this definition is like, I mean, if you have something like this, you need a well definition of this thing, right? So it's a kind of a circular definition. So even if it looks, I don't know, conceptually good, but there are some problems, so there are some issues with that definition. First of all, as you mentioned, there are some associativity laws around, and there are higher associativity rules, and this definition is kind of problematic for higher associativity conditions. So there is some issue due to higher associativity conditions. main problem is, maybe if you want to define some associativity condition by just using strict equality, so this is usually what we want, this can be done for two categories. Okay, so in general, strict n category, actually they are not equal to weak n categories, but in general, so this is a problem. Even you can really write down all possible higher coherence rules for three categories. It turns out to be very complicated. Okay, so you cannot just apply this naive definition. So this is not true in general, but except we have an exception, n equals 2. Actually, when you have a two category, you can always kind of replace associativity conditions, strict weak associativity conditions, and you can replace it by strict associativity conditions, and you can end up with equivalent two categories. Okay, so in two category level, this is nice definition, but for higher categories, this higher associativity conditions and other coherent requirements turns out to be very complicated. Okay, and also another issue. The first issue is this. So therefore, this statement is too naive. And another problem is this is a circular definition, right? So therefore, circular definition. I mean, so somehow conceptually it's a good theory, but to make sense of it, of course, you should already know what is n-1 category. So it's a kind of there is a circular nature in that definition. Conceptually good, but there are technical problems. Okay? But you can make the following simplification, at least, to get rid of the problems, coming from higher coherence conditions. Okay? Okay, so let's see. So we have a simplification. So in the sense that we assume most of the higher morphisms, let's say, invertible. Okay, so therefore we use the following notation. So let's say, so assume, let's say, most of the higher morphisms are invertible. Okay, so therefore you can deal with this higher associativity conditions in some sense. So therefore our notation for this situation is this infinity n categories. Okay, so we use this notation, and essentially this n means here, so you have some n, it means that all k morphisms are invertible for k greater than n. Okay, and then if you go back, this fundamental n groupoid example, okay, if you consider this example with this new notation or terminology, whatever, you can see that this thing, this fundamental, let's say now we consider the infinite version, is actually n, since all maps are isomorphism when n goes to infinity, so whatever it means. Okay, So since all maps are just homotopies and invertible, so these guys turns out to be infinity zero category. Okay, so this is an example of infinity zero category, and this is a very special example and very important, the most important example for infinity zero categories, because infinity zero categories are always in that form. Okay, so we have a nice fact, important fact. So therefore, infinity zero categories are not that much interesting. Okay, because the classifications are just something like this. So every infinity zero category has the form pi, I mean fundamental groupoid of some topological space. Okay, for some x in top. Okay, so it's a very important observation, and I mean because of this, actually, therefore, infinity zero categories, I don't know, behaves like spaces, okay, topological spaces. So so this infinity zero cats viewed as topological spaces. Okay, and you know that for topological spaces, there are many ways, combinatorial ways, to describe a topological space using CW complexes, simplicial sets, and etc. So therefore, this kind of motivates why these notions are also useful to describe infinite categories. Okay? This is the first important observation. But the next question, I mean the next interesting case, I mean the first interesting case when n equals 1 actually. Right? And usually we always study, I mean when somebody talks about infinity category, they mean infinity 1 categories always. Okay? Because this is the simplest possible and still interesting case. So when n equals 1, so it means infinity 1 categories or just infinite cats. Okay. So therefore, when maybe one more time, when somebody talks about infinity categories, they mean infinity 1 categories. Okay. Yeah, only. So therefore, this is the reasonable ones. So even when you choose n equals 2, things getting messy. Okay, so therefore, when people talk about infinite categories, they mean that one. So what is the properties of this thing? As you see, so all n morphisms are invertible for n greater than equal to 2. So the other way of saying this, you only allow non-invertible morphisms for n equals 1. Okay? So it's like only non-invertible one morphisms allowed. Okay? And all higher ones are just invertible. Okay? So this kind of simplified things, and then we will always study with these kind of infinite categories. And also, if you look at Lurie's and everywhere, the main objects are infinite categories in that sense. Okay? So therefore, as we did before, we propose this naive definition. Again, naive or informal. You may say an infinity n category is a category enriched over infinity n minus 1 categories. Okay. So let's focus on this definition. Okay. But actually, we will have similar problems. We have similar problems, you know, this higher associativity conditions and everything. But this happens for n equals 1. Okay, so therefore this is at least a good news. So we have the same technical problems when you have this kind of definition for n equals 1. Therefore, when n equals 1, you have a nice and formal way of defining infinite categories. Okay. But when n equals 1, actually, you can deal with these, you know, higher coherent conditions problem because all higher morphisms are invertible. Okay. So therefore, you can say something like this: an infinite category C consists of the following data. Okay? And first, you have, of course, a collection of objects as usual. First thing, and the second thing is, now when n equals 1, if you look at carefully, when n equals 1, this part turns out to be 0, right? Infinity 0. And we know infinity 0 categories are very well studied, and you have this classification. So therefore, you can say something like this: for any pairs, right? Let's say objects, this home space is an infinite groupoid. Okay, and since these guys, so since this is an infinite groupoid, because of this fact, they can be identified with the topological spaces. Okay, so so the first thing you may observe here, by the fact or the recall theorem, whatever, you can say these can be identified with topological spaces. Okay, topological spaces. And for these guys, actually, you will have, I mean, you won't have any problem with this higher associativity laws. Okay, and actually, here there exists, let's say, suitable associativity law. Okay, this is the first observation. And because of this, you don't need to worry about weak versus strict problem. Okay, so no worries, no need to worry about this strict versus weak associativity. I mean, here up to some, you know, up to weak means you always up to some coherent homotopy. And why you don't need to worry about, again, it's a nice, there is a very nice fact for these guys, just in the case of two categories. Okay, remember, in the case of two categories, so here, because Actually, as in the theory of infinite category, so the reason is similar to theory of two categories. Okay, by which I mean for any infinite category with weak associativity rule, you can replace this thing by a strict one, and you end up with the equivalent infinite category. Okay. So maybe I should write it down. Any infinite category with a coherent associative multiplication. Okay, this can be replaced by an equivalent infinite category with the strict one, with the strict associative multiplication. Okay, so therefore this general naive definition might be still problematic when n greater than 1, but when n equals 1, this is the reason we still, we are always interested with this case. You can really have a formal definition. Okay, so therefore we end up with the following two definitions. Now the definition of a topological category. A topological category is a category enriched over, let me just write C top, okay? And the C top means category of compactly generated topological spaces. And you have this Hausdorff condition as well. This is the category of compactly generated topological spaces. So therefore, this is the and enrich over that means your home space for all xy is a compactly generated topological space. Okay. Good. And finally, you can formally have the following way of defining infinite category. And infinite category is a topological category. Okay, that's all. This is our final definition. Okay. So the second and finally a formal definition, we define an infinite category to be a topological category. Okay. And as you see, this is kind of not quickest, but let's say quickest and more transparent way of defining infinite categories using topological spaces. I mean, I don't know, conceptually good, but technically it's really hard to work with. Okay, difficult to work with. Okay, so therefore, but since you view an infinite category as a topological space, let's say, we know that the theory of topological spaces can be combinatorically, right, studied by using the language of simplicial sets. So instead, more combinatorial way is the use of simplicial sets. Okay, so I guess for next time I will essentially present how one can study infinite category as a simplicial, as a sort. One can define an infinite category to be a very particular simplicial set, what we call weak Kan complex. Okay, and we will see how this kind of simplicial picture helps us to encode the same information. Okay, this maps between maps. But of course, I'm not going to prove why these approaches are equivalent, but they are all equivalent notions or equivalent definitions. But as I just told you, this one will be more, gives us more combinatorial tools. But maybe I should stop now, and next time we will study these things.
Any questions? You will use this finally in algebraic geometry or in which area? No, in the next talks.
Eventually, we want to discuss derived algebraic geometry context.
Yeah.
Okay, so we will study all of these things to make sense of the main objects, emerging in that area, like derived schemes, fine derived schemes, and everything.
You will remind us these things.
Sure. Of course. Yeah. There are other talks. So next time we will see the simplicial point of view, and then we will build, some background for these things, everything. I find derived schemes and everything. But to do that, I mean, in practice, since we are not going to prove anything, I mean, we don't need this fancy infinite categorical techniques. So we can always think, the infinite categories like usual categories, because we are not going to prove anything. But essentially, everything is happening within the framework of infinite categories. So at least we need to know what's happening here behind the scenes. But later, we'll see. We will construct the spaces, and then we will construct geometric structures on that spaces. And for instance, can we do symplectic geometry on those things? Or can we do contact geometry on those things? So we will try to answer those questions, and I will mention several interesting results.
So you said weak Kan complexes, are they quasi-categories or?
Quasi-categories, right. So in that case, you can either say infinite category or quasi-category. So weak Kan complexes, so not a strict Kan condition, but so I will come to that. I will explicitly write down what is weak and a strong Kan complex condition. Essentially, if you are familiar with these things, so a short spoiler, you want to extend all possible horns, right? To the maps like that. Okay, so it's like you want to fill the diagrams like this to that form. Okay, but not necessarily. Sometimes it is unique. There is a unique way of doing that, unique way of extending this map from horn to N complex. But we will see how those things are connected. But a very small spoiler, it's like it is your map, right? So you want to try to define composition, okay? And existence of these things tells you that you can always find this compose map, not necessarily uniquely in infinite categorical setup, but it means that you can define composition. It basically encodes this information if you want to connect this topological version and that version, but we will come to that. Okay? So this Kan condition, weak Kan condition, this is true for all I, but for inner horns, we are not considering the outer horns. So, for instance, when n equals 2, this is the inner horn. This is the outer. I'm just erasing one edge and erase the inside. And these are all possibilities because this is your 2 simplex, right? This is your 2 simplex, delta 2, geometric realization. And the horns are, for instance, this one is A21, A2. So if this is your 0 vertex, you erase this part. Anyway, so there's some language and terminology here. But of course, if you think these things like vertices are like your objects and the edges are like your maps, I mean, of course, here you don't know the existence of this thing, right? But this one really corresponds to defining composition. Okay, so this is the reason we are interested in inner horns and etc. So there are some other technical details, but this is the logic more or less. Okay, so infinite category is a weak Kant complex. This is the end of the story and a spoiler. And next time we try to understand why.
How new is this the sequential approach compared to the other two you gave at the beginning?
So they are actually not that much new, I guess.
Just people came up with all these three setup at the same time.
I mean, I guess, I mean, we will discuss these things, but in algebraic topology, you know, there are nice, I mean, maybe since Quillen, maybe once you realize there is a Quillen equivalence between top and simplicial sets, right? In which sense, maybe these discussions and the interaction between that kind of interpretation and this one goes back to this, I don't know, Quillen's constructions, maybe, I don't know. But these are not that much new things. I mean, these 50s and maybe 60s. I don't know, but this, I mean, combining everything into suitable framework, this one is kind of new, even if some ideas and techniques can be easily seen, you know, partially in the literature. But this formulation is like, I don't know, 2005 Lurie's thesis, PhD thesis, I guess. And parallel to that one, there is this homotopical algebraic geometry. Homotopical algebraic geometry by Tuan and Vezzosi. This is also goes back to, okay, I don't remember this one, something like this. But all techniques partially already exist in the literature. But these ideas, I don't know the exact history, but my guess is maybe it goes back to this kind of interaction between topology and simplicial sets. Okay.
Okay. Well, thank you.
Thank you.